In this video, we will present our work IllumiCraft, Unified Geometry and Illumination Diffusion for Controllable Video Generation. Let's focus on the motivation. While there has been significant advancement, previous video relighting methods omit explicit geometric guidance, losing lighting fidelity and temporal coherence when scene geometry changes, and lack the comprehensive video dataset annotated with both illumination variations and 3D geometry cues. IllumiCraft fills both gaps. It unifies illumination and geometry guidance for text and background condition video relighting. Releases a benchmark dataset of 20,170 paired videos with diverse lighting conditions and 3D tracking videos, which can support video relighting and broader controllable video generation tasks, and outperforms state-of-the-art methods in visual fidelity and temporal coherence. Given a prompt and input video, IllumiCraft edits scene illumination conditioned on the static background image. It handles a variety of illumination scenarios, including spotlight effects. For each input video, IllumiPipe produces 5 outputs, HDR maps, detecting a chrome ball in the first frame with diffusion light and estimating HDR for all subsequent frames, see Appendix, foreground and mask videos. Segmenting the first frame with grounded SAM2 and then running Mad Anyone across the entire video using that initial mask. A relit video, feeding CogVLM2 video Llama 3 chat captions, augmented by a sampled lighting prompt, see Appendix. Into light a video applied to the foreground video, a background video, and painting masked regions in the original footage with Diff Eraser, and a 3D geometry video extracting per frame geometry via Spatial Tracker. IllumiCraft unifies illumination, text, appearance, and geometry in a single diffusion transformer. HDR maps are encoded into features by a trainable lighting encoder and added to learnable illumination tokens. The HDR map features are dropped with 50% probability during training to simulate missing HDR input, then concatenated with frozen text embeddings to form the prompt. Relit videos, reference images, and 3D tracking videos pass through a frozen VAE encoder into appearance and geometry latents, which with injected noise flow through the DIT. A lightweight conditioned DIT clones early DIT layers, projects geometry latents via zero initialized linear layers, and adds them hierarchically. Finally, a frozen VAE decoder reconstructs frames whose lighting faithfully follows text instructions, scene context, and 3D geometry. Using 2.11.3b DIT as our backbone, we freeze the VAE and clip text encoder to preserve pre-trained priors, and fine-tune only the DIT blocks and zero-initialized linear layers for stable integration of appearance, geometry, and illumination. At each diffusion step T, we condition on the noisy video latent, geometry latent, control latent, and prompt embedding, then minimize the diffusion loss by predicting the added noise. We curate 20,170 high-quality, free-to-use videos from Pexels. To simulate missing inputs at inference, we randomly drop HDR features, 50%, 3D, tracking data, 30%, or reference images, 10%, during training. Models are trained for 3,000 iterations on 4A6000 GPUs using Atom. The learning rate is 0.0005, and the batch size is 2. The whole training time requires about 90 hours in total. Under text-conditioned relighting, with only a foreground video and a text prompt, Isolight over-smooths fine details, such as rabbit fur. NEV2V introduces color distortions, and light a video blurs details and dampens contrast. By contrast, IllumiCraft preserves textures, captures subtle lighting nuances, stays prompt faithful, and produces coherent videos. With background conditioned relighting, existing approaches suffer color shifts, exposure mismatches, and oversmoothing, even on scenes like a sunlit sea or backlit figure. IllumiCraft, by contrast, delivers prompt faithful lighting, sharp subject, background separation, and realistic textures for the most photorealistic coherent results. IllumiCraft leads on all standard metrics. In text-conditioned relighting, it achieves the lowest FVD, highest perceptual quality, sharper visuals, stronger prompt alignment, and temporal stability, outperforming IC Light, NEV2V, and Light a Video. In background condition tests, it dominates both 16-frame and 49-frame sequences. On 49 frames, it cuts FED by 37% versus Light a Video while boosting perceptual similarity, prompt fidelity, and temporal consistency. On 16 frames, it surpasses relight vid across all fidelity and detail metrics. Next, ablations show that adding geometry guidance to illumination-only training consistently boosts all metrics. Across HDR drop rates of 40 to 70%, a 50% drop delivers the best balance of FVD, prompt alignment, and temporal consistency in both text and background condition settings. Dropping tracking videos at 30% and reference images at 10% during training yields the best balance of visual quality, prompt alignment, and temporal consistency across both text and background condition settings. We present additional video relighting results that exhibit high fidelity, prompt-aligned outputs, fine detail, and stable temporal consistency. Failure analysis reveals two issues. On a misty, chalky-lit castle, misaligned foliage yields oversaturated greens, and when a flowering branch includes an LED floodlight, the light is misclassified as foreground, altering its appearance. We'll address these by expanding our dataset with more dynamic occlusions and strong directional lighting scenes. Thank you for watching this video.